Welcome to another episode of Out of This World. Matthew Nicolantonio and Scott Sutherland, meteorologist and science writer. Today, we are talking about a planet specifically that has given us a lot of interesting science fiction recently. Former home of Matt Damon, Marvin the Martian. We are, of course, talking about Mars, the red planet, and a lot of sort of recent, or maybe not renewed, but oncoming interest in getting humans to Mars. We'll talk all about that and the technology that has been there. But Scott, let's simply start with this.
Right.
Why the fascination with Mars, studying Mars, and potentially getting humans to Mars?
Basically, when it comes down to Earth's position in our solar system, Mars is the easiest planet to get things to and study. Venus is technically closer, but getting something onto the surface is extremely difficult. It's a pressure cooker filled with acid, basically, in that atmosphere. And so things only last minutes, maybe an hour at the tops.
Right.
So Mars is much more accommodating for our landers and rovers and so forth. But it's still reasonably easy to get to, reasonably easy to communicate with from Earth. So it's sort of the ideal, closest location for studying another planet to get a different perspective on how planets develop and maybe even give us clues to why we're here. And maybe find possibly life there, either that...
It seems to have always been the goal.
Yeah.
Was there life on Mars?
Exactly, right.
All right. I mentioned it's the red planet.
Yeah.
Why, or do we know why it is red?
We do. It's because the soil, the surface layer of Mars contains a lot of iron oxide, which is basically rust. It has rust particles in the soil. And the Martian sky, if you were happening to stand on it, would look pinkish because the dust particles also contain iron oxide. And so as these get lofted up in the air and fill the atmosphere above you, it washes out what, our normally blue sky appears pink in there. So, but that's the basic reason is these rust particles that just permeate the soil there.
All right, let's talk about weather.
Right.
What sort of weather, if any, is there on Mars?
For only having around 1% of the atmospheric pressure of Earth, Mars, surprisingly, has a lot of Earth-like weather. There are clouds there. We've seen them from orbit. We've seen them. It's actually easier to see them from the photographs the rovers and landers take looking upwards because you can see the cirrus clouds passing over these areas. And they're a little difficult to make out with that dust in the air, but they're some days they're very noticeable. There's actually a dedicated camera on the Perseverance rover that takes pictures of it's called Skycam. And it's there to take pictures of the clouds to sort of track them and monitor them just to see what kind of Martian weather we deal with on a daily basis, or they deal with on a daily basis. But you can't have rain. You will never see rain clouds on Mars. But there has been snow.
So how, maybe explain the difference, why you're able to get snow but not rain.
Right. So the snow was detected in 2008 by the Phoenix lander, which was closer to the pole of the North Pole of Mars. So it was colder there. It was definitely water ice that formed this snow. It wasn't carbon dioxide snow, just based on the temperatures at the time. And it was like virga. It never reached the ground, but it was detected by the LIDAR, this laser distance, sort of like radar using lasers instead of radio waves, that was beaming up into the air, and it caught these streamers of water, ice, snow falling from the clouds that were up there. But again, it didn't reach the ground, but they had solid evidence of this happening. And basically it's because ice can actually survive at lower atmospheric densities than water can. Like I said, with only 1/10 the atmospheric density on Mars, water just can't really exist there in a liquid form. It'll evaporate immediately and disassociate in the air and so forth. So, but the ice particles, as soon as they form and they freeze, that solid surface gives it a bit more staying power, I guess you would call it. So it can last longer. And we know that there's snow at the poles because there's the huge carbon dioxide polar cap at the southern pole. There's a water and carbon dioxide ice polar cap at the North Pole. So there is snow, there is ice that forms and stays there at sufficiently low temperatures, but we will probably see more snow if we put more of those sensors on Mars, closer to the poles. But yeah, it's we see clouds, we see snow. But
do we know like sort of what the temperature? Like, is it's colder than?
Yeah. I mean, sort of midday at the equator on Mars, you can get up to maybe plus 20 degrees Celsius, maybe a little bit higher than that. But it can get down to like minus 70 degrees Celsius at night.
Right. That's still at the equator.
The equator, yeah. Right. Now, when you're really dealing with the poles, you're getting down to like minus 170, minus 170. So it gets significantly colder there. So there are days that we look at it and say, hey, Winnipeg is warmer than Mars, or colder than Mars. And it's done in a tongue-in-cheek joking way, but it's true on that one day.
Yeah.
At the equator, or at where a specific rover or lander happens to be located, which is, again, mid-latitudes or near the equator. But then we always have to make the point, so much more colder at night, so much more colder at the poles. So, it's all relative.
Right.
But it does tell us that if we were to send people there are conditions where they would be fairly comfortable. I mean, you can't walk out not wearing a spacesuit, but the temperatures would be somewhat comfortable for people to be there on the surface during the day walking around.
What other similarities in terms of maybe topography does Mars have to Earth? Martian volcanoes?
Yeah, there are several Martian volcanoes. They're very noticeable from orbit. There's 4 of them, I believe, that are very noticeable. With Mount Olympus being the largest of them, Olympus Mons. But they actually just recently found a new one, where right at the western end of the Mariner Valley, the Valles Marineris, there's all these weird crags and crannies in the rock that they figured out was actually volcanic in origin, and actually showed what was a volcanic caldera at some point in the very, very distant past. So it's this extinct volcano that existed at the end of that large crevice in the Martian topography. But yeah, these volcanoes, they get so big, and they're some of the largest in the entire solar system, mainly based on the fact that Mars doesn't have any plate tectonics. So if there's a volcanic plume there, it can't move, whereas on Earth, we have so much plate tectonics going on that the magma chambers can move underneath where a volcano is and cause it to go out. It just kept going and going and going and building up this larger and larger volcanic mountain until it finally just cooled off enough that it stopped.
All right, let's talk a little bit about gravitational pull and the sort of the difference of how much a person might weigh on Earth versus on Mars.
Right. So Martian gravity is a little over 1/3 it is here on Earth. Mars is a smaller planet than Earth is, so it exerts less gravitational pull. It's about 3 point something meters per second squared compared to almost 10 meters per second squared here on Earth. So you would feel significantly lighter as you were going around on Mars. In fact, it actually might be, if you were standing on Mars and moving around, it actually might be easier for you to skip around as the way you move rather than just walking, because it would be more efficient, I guess is the best way of putting it, way of moving along instead of running or walking, is taking these little hops as you go, and you would cover more distance and use that lower gravity to your advantage.
Interesting.
Yeah.
All right. One more point here about our sort of lesson about Mars before we move into missions and stuff like that.
Right.
Sols. Those are sort of the equivalent of an Earth day, but they're not the same amount of time.
Right.
And that's maybe when we started studying Mars, caused some issues with people who were observing the planet.
Yeah. So a Martian sol is just short for solar day.
Mhm.
I mean, that's the same thing we measure here on Earth
Yeah.
is a solar day, but we call it a day.
Mhm.
There, to differentiate it, because it is different, we call it a sol, S-O-L, and it's actually a little bit longer than the day on Earth. It's 24 hours, 39 minutes, and I think about 35 seconds long. So basically every day on Mars, every time the sun is up, it's about 40 minutes later than it is here on Earth. And so you have to kind of account for that. Actually, sorry, it's 40 minutes earlier than here on Earth. So we have to account for that. If you want your scientists and your engineers up at the same time that the rovers and landers are doing most of their operations, they have to adjust their personal working clock back 40 minutes every time to sync themselves up with the best time to be doing all these operations on the planet. So if you are a scientist working at NASA's Jet Propulsion Laboratory and you're supposed to keep track of the Perseverance lander, then yeah, you're going to have to go in earlier and earlier and earlier during the day until you're going to be way off from everybody else who's working at the same installation or the same building even.
All right, let's talk a little bit about some of the missions that have started to explore the planet. When did we start sending rovers to Mars? And when we did, what were the purposes of those missions?
Right. So the first times that we landed there, we're talking like the Viking landers way back in the 1976. The first rover, though, was the Sojourner rover that landed in 1997 with the Pathfinder mission.
Okay.
So this was basically like a tetrahedral lander that landed encased in balloons, that it hit the surface and bounced several times. It came to a rest, sort of, flowered open, let the rover drive out for a little ways away. It was tiny, like a little remote-controlled car almost. And it only went a short distance away, roved around a little bit, and then the mission ended. Since then, rovers have gotten larger and more advanced. We had the Opportunity and Spirit rovers that launched in the around 2000. They arrived around 2005 on Mars. They operated for years. I think Spirit was there for 8 to 9 years. I think it was in operation for until it got stuck, and then it had to end its mission. Opportunity went for over a decade. Like it's so far still the longest running rover on another celestial body that we've ever operated. And its mission ended a few years back when we had the massive planetary white dust storm, and it was a solar powered rover. So eventually it just ran out of power, and it was so old that its batteries couldn't maintain it, and its mission ended. Now we have Curiosity and Perseverance that are nuclear powered. They have a nuclear battery on the back that it generates power based on nuclear decay that creates heat, and then that heat differential creates the electricity, and then powers the rovers. And those can operate effectively indefinitely, as long as if we're talking decades, 20, 30 years, as long as the rest of the rover is able to maintain its wheel integrity and so forth. They found that water was water that could have supported life. It was neutral pH. If you were there at the time, you could have dipped a cup in and drank it with no problem.
So in terms of those ongoing missions, what are they studying right now, or what are they hoping to find out as we work towards potentially getting people to the planet? Right.
So the main focus of the rovers has been to investigate past conditions on Mars. There have been clues from that they've seen from orbit and so forth, and with some of the lander missions, that Mars may have been more Earth-like in its distant past than we realized just looking at it through telescopes and so forth. And that's been played out with each successive mission. The Spirit and Opportunity found tiny little hematite nodules, like little spheres that they call blueberries because they look blue.
Right.
And those are created by water. You have to have minerals in contact with water to create hematite. And then as the missions advanced, they found, okay, well, we want to test the soil, the sediment layers and so forth in the Martian soil to see what kind of water was this? Was it something that we could have, was it good for drinking water? Was it really acidic and so forth? So could life have existed there? And again, curiosity and opportunity sort of combined their different scientific investigations from different parts of the planet, and they have determined that yes, Mars was warmer and wetter, and it had liquid oceans, liquid lakes, and so forth. So all the low topography in the northern hemisphere was probably a huge ocean, and they found that water was water that could have supported life. It was neutral pH.
Right.
If you were there at the time, you could have dipped a cup in and drank it with no problem.
That's easier said than done.
Easier said than done, yeah. So it was an environment that could have supported life.
Right.
And so now the missions are sort of focused on was there life?
Right.
I mean, everything we've seen here on Earth, life will develop in all of the environments that we have found so far, from the most extreme cold to the most extreme heat, extreme acid, everything, the deepest layers, the deepest caves we find life everywhere. So there doesn't seem to be any reason why Mars wouldn't have done the same thing.
Okay.
And then just over the millions of years since it was that warmer, wetter environment, it lost its magnetic field, it lost most of its atmosphere to the solar wind, and it just became the dried out, cold environment that we see now. But there's nothing to say that there couldn't be life still, if it developed there, still existing under the ground.
Okay.
In glaciers, because we know that there are deep glaciers underneath the soil there that are just vast resources of fresh water. And we have life in Antarctica. Why not something there, right?
Right. Okay, so let's talk about what would be the obvious next steps beyond rovers is getting people to Mars to further examine the planet.
Yeah.
We know that a lot of the upcoming lunar space travel is with the intention of hopefully getting from Earth to the moon to Mars.
Yeah.
But all right, let's start first and maybe work our way backwards a little bit. Realistic timeline of when it might be possible for humans to get to Mars.
Right. So if NASA had the kind of budget that they had for the lunar missions
Always
back in the
comes
60s
down
and
to
70s, it always comes down to money. If they had that budget, that take it all and make it today's dollar value, if they had that level of budget, we wouldn't need to go to the moon first.
Right.
They would probably already be on Mars.
Right.
The science fiction of For All Mankind isn't really all that far off. If NASA had continued to have that kind of money, we probably would already be there.
Mm-hmm.
Now, because they have less to work with, we have to take a slower approach. So first the moon, establish something there, use the moon as a jumping off point. So we're talking probably the early 2030s, maybe 2032, 2035, that we might see a mission launch to go to Mars. But we have a lot of technological hurdles to overcome before we can do that.
Is fuel at the top of that list?
It is. We can generate the fuel, but it comes down to how do we allow the spacecraft to keep enough fuel to get there and back after launching it from Earth. So that may be something where we launch from the moon.
Right.
We build something there, we fuel it from water that we may find on the moon, and thus we sort of remove Earth from the equation as far as that goes, to make it easier to get there. From there, it's a matter of how do you keep your astronauts safe from space radiation? And
from each other.
Exactly. How do you keep them sane?
Because it's a long journey, even from the moon to Mars.
Yeah, it's right now a mission takes about 9 months to get from Earth to Mars.
Yeah.
I think that they would want to first get that down maybe to 6 months.
Right.
Your average International Space Station mission right now is about 6 months. On the higher end, out to a year as the long term. So, they want it between 6 and 9 months. But that's a very small confined space to be in, with maybe half a dozen people. They do it on a regular basis on the ISS, but they have Earth to look at out their window every day. Out in space, you're not going to have that. So how do you keep people mentally healthy? How do you keep them physically healthy? How do you keep them fit on that kind of a journey? We don't have cryogenic freezers like they do in science fiction.
Yeah.
So, how do you grow? Do you grow food on the way? How do you have water? How do you keep backup systems so that when these things fail, which things seem to inevitably do, how do you keep everything safe? How do you keep the astronauts healthy for when they get there so that they can actually do the work they're supposed to, and then get them back?
Yeah, that's
right.
I want to talk
Exactly.
about that. That would be a pretty big challenge too. It's another, long journey,
Yep.
more fuel needed. So that's sort of like when we talk about these rovers, they land there and then they don't come back.
No.
So how much of a challenge, or, do they know yet how much of a challenge it might be a return mission from Mars, since that hasn't really been done yet?
Right. So for this, we can kind of look to science fiction a little bit, like we mentioned before, like The Martian.
Yeah.
In The Martian, Andy Weir did a lot of research before he sent this out. It's one of the most scientifically accurate science fiction novels out there. And the whole concept of their human Mars missions was to send like a spacecraft, a rocket that will land on Mars like 4 years ahead of time, so that it can just sit there and generate fuel in its fuel tanks using systems that we've already tested on Perseverance for generating oxygen, and create enough fuel so that rocket, when the people arrive at that location, can then do all the experimentation they need to, climb into that rocket and leave on it. And that will get them back up into orbit and to the spacecraft, which would be like almost like a ferry that would get them from Earth to Mars, orbit Mars for a little while, wait for the astronauts to come back up to it, and then leave Mars and go back to Earth around the sun. So that kind of architecture for the human Mars missions makes a lot of sense. Like, you have one dedicated spacecraft that gets you there and back, and then you have secondary spacecraft that you would launch just a normal launch from Earth to Mars, like you would do with any rover or lander. And then that becomes your supplies and that arrive early, and your rocket for returning back to space once you get there.
So they're growing potatoes on Mars.
Right.
Realistic?
Sort of. There are limitations because the Martian soil not only contains rust particles, it also contains a chemical called perchlorate, which is a toxin to human nervous system. So you have to be really careful with that. Like, if you watch the movie, it seems as though he digs a certain distance underneath the very topsoil to get the ground that he brings in, which that probably makes more sense.
Okay.
You probably couldn't drag the soil off just right off the surface in. It would have too much contamination. So you could probably get the soil in using our own waste as a fertilizer. I mean, that does work. Would it work in Martian soil?
To be determined.
To be determined, yeah. But it's feasible. Everything that's done in the novel and in the movie is at least feasible.
Right.
But yeah, we're really going to have to test these things to make sure, to see, like, what do we need to bring with us when we go there. We may actually grow the plants on the journey there, and bring them down with us, and then, lay them out and so forth in the habitat, and then actually have them there. And then it's just a matter of what they produce and for how long that can help sustain the astronauts while they're there.
All right, last question before we wrap up here.
Right.
Of everything associated with sort of this Mars project, what interests you the most that people are or that teams are researching that you want to know the answer to?
My big focus for all of this is that question of is there life on Mars? Was there life on Mars? Because we know that the environment was at least friendly to that at millions of years ago. So I can't see why there wouldn't be something that developed there. I would be shocked if it was just a barren, dead planet,
right?
Even with those environments back then. But then life being there now, that's my big thing now, is that there are environments under the ground that could very easily support the microbes that we know about here on Earth. So, so when are we going to find it? And what does that do to Mars exploration? Because we have this idea that we don't want to contaminate any life that may be there. We take very much care for the missions that do go look for life, not to send Earth life along with it to contaminate that. So what kind of changes will that make to not only how we explore Mars, but our own view of what where our place is in the universe? Because we won't be the only life that we know of then. So,
all right.
Yeah.
So lots to look forward to as these missions continue. As we mentioned, decades into the future that we're going to be continuing to be following. Scott, thanks so much for being with us here today.
Yeah, this was great.
It's very pretty out here.